So our next talk is going to be improving retrieval from the OVS Hashmap. And our speaker is Rosemary O'Riordan. I'm sorry, I can't pronounce that properly.
It's all good. It's
Go
a
for
hard
it.
name. Okay. Hello, I'm Rosemary. I work at Red Hat. And today I want to talk about why try to improve OVS's Hashmap, what the current Hashmap looks like, the improved design, and results and next steps. So the Hashmap is used all throughout OVS and OVN. There's multiple data structures built on top of it. It stores a lot of options in config. And for OVS and OVN, it stores some of the most fundamental aspects, like the logical flows and data paths in OVN, for example. And then here's just some greps for the HMAP for each iterator and mentions of HMAP. You can see there's a ton. So this is the current design of OVS's Hashmap. You have buckets where you have the first node, which does not contain any data, and then following that, it's a singly linked list of nodes that are embedded inside of the data, which is the element. And it's worth noting that when you insert a node into the Hashmap, it is inserted at the front of the list. So it's O1 complexity. And the idea for this redesign came from this Valkey article by Victor about their new hash table, where they were able to achieve 20 bytes less memory use per element. So that's pretty significant if you have a really large hash table. So this is the improved Hashmap design. We have, instead of there being a node at the start, there's a bucket which points to the node. And if we keep adding elements, we can see that the nodes are no longer in a linked list. The bucket is pointing to the nodes. So we can keep adding them. But now if we want to add another, let's say the bucket has used up all of its pointers. So where do we put this one? Well, we can create a child bucket, which then that top right one is moved to. And then this child bucket would be able to do the same thing. So it can keep going layers and layers down. I didn't want to make a super crowded graphic, but yeah, that's the idea. And then inside of the bucket, there's some metadata and then the actual pointers. So on the right, there's 7 pointers. And on the left, there's 8 bytes of metadata. Inside the metadata, there is a bit. Oh, it's covering some of the text, but the first bit is to indicate if the last node is a pointer to a child bucket, because as I showed in that last graphic, you can move the last node to the child bucket. So that last pointer can vary if it points to a node or another bucket. And then there's presence bits that indicate whether each entry slot is full, which makes sense. And then there's 1 byte of hash for each entry. And here's an example of what it looks like actually filled in. If we just have 1 entry in this bucket, you can see that it's in the 5th position. So there's an actual pointer there. And then the metadata, the chain bit's unset because there's no child bucket. There's the 5th bit set in the presence bits, and then there's 1 byte of hash in the 5th position of the hash byte array. So the pros and cons of this design would be that it saves space in the cache. I should have mentioned that this, you can see it's 64 bytes. So this is a cache line, and it makes a lot of sense that you would want this to be persistent in the cache, because for iteration, like if you're iterating by hash, you're going to keep having to compare the hash of these nodes repeatedly, and that can cause a lot of cache misses. Because if you no longer have the hash present in cache, then you have to go look it up in main memory, and it takes a lot more to do that. So if you can keep this whole cache line present in the cache, then you can just compare that 1 byte instead of comparing the entire hash, and then you immediately know if it's not a match. And yeah, because of that, less cache misses. There's no need to loop through each node to remove. So like with the previous hash map design, if you had a bucket with a lot of nodes, you would have to go one by one by one. The way that the OVS Hashmap is, it does balance each bucket to only have an average of 2 entries, so it's not that many, but still something to consider. And then this is something Valkey said, I didn't personally verify, but they found that there was a less than 1% chance of a hash byte collision, which then would likely lead to a cache miss, because then you'd have to actually look up the full cache. And the cons are that it's a lot more complex. It just adds a ton of logic. The current hash map is like super, super simple. A lot of the functions are one-liners or a couple lines, and this adds a ton of logic and makes it a lot less readable. But here are the results. So it didn't go, well, okay, this is sort of the first draft, but it actually did get slower. So don't use this one. But yeah, as you can see, the rest, the iterate, search, and destroy aren't terrible, but the insertion got a lot slower. And I think that's mainly because that child bucket logic is just so much. And it's like, ideally, there would basically be no child buckets, because you can change the in the mass calculation function, you can make it so the average number of nodes for each bucket would be 6, so that then it's a bit less likely that there's gonna end up being child buckets. So you wouldn't even have to do all that logic, but the way I have it right now, that's all in the insert function. So it's just a lot of code that's probably not being touched and that should be moved out of there. But yeah, these were with 10 million nodes and removing 50% of the entries on search. And the next steps are definitely optimized. I want to keep working on this. This is a really common hash map design. Like tons of organizations have had success implementing hash maps like this. So it is interesting to keep trying to get it to work. Definitely avoid running the child bucket logic as much as possible. And maybe see if the last pointer always being to a child bucket is more efficient, instead of having to move that last node from the parent bucket to the child bucket if it gets full. So that is just something to think about. And yeah, that's it. Thank you.
Are there any questions? I see one in the back. Yeah.
Thank you. So we brought it up right at the end, but I was wondering what was the motivation for putting the logic about moving the last element of the bucket to the new child bucket instead of from the very start, like proactively creating the child bucket instead of.
Yeah. I mean, I guess the reason would be that then you just have one extra spot where you don't have to make, you don't have to go another pointer further. So instead of, you know, in this case, it's like there's 7 options in the first bucket to store an actual node instead of just 6. So it, you know, it just allows you to store more nodes in each bucket, basically. Unless you have a child bucket, of course, but assuming you don't, because you most likely, hopefully, won't most of the time.
Right. Thank you.
Mhm.
One more question there.
Yeah, we've seen the performance benefits, but I think I missed the memory optimization benefits on the slides, because you said it's 20 bytes per entry, and how it's in the testing scale.
Yeah, that was just Valkey's metric, that they found that they were able to reduce memory consumption by 20 bytes per element inserted.
I guess this is the biggest benefit, right? So.
Yeah. Yeah. Exactly.
I don't see any other hands raised. Oh yeah, there's more questions. Yeah.
So you mentioned this is Valkey's Hashmap, and you aim on doing further research into removing some conditional logic to just speed up the arithmetic. Have they done any research into this and how viable that is in improving the search and destroy and insert times?
So this design was just looking at an article they published. So I don't actually, I don't think I can actually look at their code to see what they've done. And they didn't mention in the article anything that they did. So I was just trying to adapt their design to the OVS Hashmap. But there's a lot of other designs very similar to this that have articles written about them. Like I just recently saw that Datadog did a similar thing to their hash map and posted an article about it. So I'm definitely going to keep looking into things like that and seeing if anyone else has better ideas for that.
Regarding your further testing and investigation, will this just be posted in the OVS mailing list? Because this is interesting. I would like to follow along.
Yeah, I mean, I'm not going to post it unless it actually improves the hash map significantly. But if it does, then definitely. And if there is a significant improvement, I'll probably also write a blog about it maybe, so I could share that.
If that isn't, could you also, because I'm interested.
Okay, sure.
Okay, thank you.
Yeah.
So a few more questions here.
Delaying lunch.
Yeah, I was curious if you did some measurements of population sizes in all the hash maps that are currently used. Do you know if there are statistics about that?
In operation sizes?
Yeah. For example, in typical deployment, generally, what size of hash maps do we see?
Oh, you mean like number of nodes?
Yeah, no.
Yeah, I did that. I didn't put it in this slide, but this 50% average was calculated by, I tested with a bunch of different size nodes, a bunch of different size mutations. Like this one is removing half the nodes, but I also tested with removing 10%, removing 90%, and just came up with a general about 50%. But I only included one example because, yeah.
It's a nice subject. I would suggest also looking into vStable, which is another alternative version.
What's it called?
vStable.
Okay.
VRSTable.
Okay, cool. Thank you.
It's a nice version implemented in C, but using open addressing.
Thanks.
Hi. You said that there is some complexity about insertion with the
Yes.
child bucket. Do you have the same complexity in the story while promoting and destroying the child buckets?
Oh, you mean storing a node in the child bucket? Is there that
No, I
same?
mean, let's say that you insert, and then you created a child bucket, and then all the other ones not in the child got destroyed. So now you have just a child with no other direct nodes. So that now you can promote the child and get rid of it.
Oh, yeah, that is, I mean, that's another interesting thing to consider. Like, what happens if you have nothing in a, yeah, that's actually a really good idea. If you have nothing in a child bucket, you might as well get
No,
rid
the
of it.
opposite. You don't have
Nothing in
anything
the, oh, in the top one,
Yeah.
and then, oh, yeah, that could be a good idea. That's a good idea of something to try for me to see if it gets better. Yeah, thank you.
Thank you. Let's thank our speaker again.